Come on, here we go. So these last two are going to be finding extrema and inflection points. So essentially everything from 4.1 and 4.2 in one singular problem. So here we go. So remember, for finding extrema, remember that's our maxes and mins. The first thing we always need to do is find the derivative. So let's do that. And let me actually do this correctly. So the derivative, this is technically a product rule, so I'm kind of come over to the side over here because I'm going to run out of space if I don't be careful about my spacing. And do my little product rule chart over here. So we have x times e to the negative x. Derivative of x is 1. E to the negative x is technically a chain rule, so we get e to the negative x times the derivative of negative x, which is negative 1. So if we put that together in our product rule, f prime g plus fg prime, 1 times e to the negative x, so e to the negative x, plus x times negative e to the negative x. I just swung that negative to the front of the e to the negative x. So essentially e to the negative x minus x e to the negative x. And then the one thing I suggest for these is always triple check and see if you can pull anything in common out. So here we have an e to the negative x in common between all of them, all of the two terms. So let's go ahead and pull that out. So we'll factor out an e to the negative x. We'll be left with 1 minus x. And the reason for doing that is it makes the next step of setting the derivative equal to 0 a little bit easier. Always just try to factor out your greatest common factor. So our next step, as I just kind of said, is remember now we have to find our critical points. So we need to set the derivative equal to 0, and we need to talk about whether or not the derivative is ever undefined. I want to talk about undefined first. And actually, let me remind myself how much space I have and try to. I probably want this much space for the inflection points. So is this derivative ever undefined? Well, remember that in our case is this if we have a denominator. Yep. And if that denominator would be equal to 0. So in this case, we technically kind of do have a denominator. It's a very sneaky denominator. Notice we have e to the negative x. And remember, a negative exponent means that it would be a positive exponent in the denominator. So technically we do have a denominator here, so we should consider it. But one super nice thing about e to the x, we're e to the anything. I don't care what that thing is. It can be absolutely anything. As long as there's not a negative in the front, that's different. But e to the anything is always greater than 0. And maybe I shouldn't use those types of brackets if I'm going to have a greater than symbol in what I'm writing. So e to the x, or e to the anything, is always positive, always greater than 0. So hopefully that reshared correctly, Delaney. Let me know if it did. So that means that this derivative is never undefined. So we've considered it, but it never happens, so we move on with our lives. Now let me jump back to the derivative equal to 0. Now technically I just rewrote it as 1 over x times 1 minus x over e to the x. But I'm going to forget that I rewrote it like that, and I'm going to consider it in this case, just for giggles, because I want to. So here, if you still think about it as e to the negative x times 1 minus x, we have a product of things, so one of those two things must have been 0. But again, e to anything is never equal to 0, so that never happens. And then we get x equals 1 from the other piece. So we found the derivative, we found our critical points, we just have one of them, x equals 1. And now we need to do either the first or second derivative test. Now, since we're finding the second derivative for inflection points, this might be an okay place to use the second derivative. But I'm going to go ahead and just use the first derivative test because I think that's what most people default to anyway. So I'm going to finish out with the first derivative test. If anyone really wants to see the second derivative test, I could do it, but let's start with the first derivative test at least. So remember with that, we put it on a number line and we choose test points. I'm going to pick 0 and, I don't know, 2. Let's not be too crazy. So we take those points, plug them into the derivative. So we want f prime of 0 and f prime of 2. I'm going to kind of walk through that sign way that I was kind of talking about the other day, and then I'll find the actual number. But remember, if you can just figure out the sign of it without actually figuring out the number, you can totally do that. So if we think about what we would get if we plugged in 0, we would get e to the 0 times 1 minus 0. So the 1 minus 0 would, of course, be 1. Now, I've already said that e to the anything is greater than 0. So that whole thing is going to end up being positive. A positive times a positive. Or if you're curious, it just does come out to be equaling 1, because anything to the 0th power is also equal to 1. But anyway, so that's a positive. So when we plug in 0, we get a positive value. So I'm going to go back to my number line and put a really obnoxious plus sign. That's too obnoxious. Put a plus sign above my 0. And then if I plug in 2, we'll get, oh my goodness, we'll get e to the negative second times 1 minus 2, so e to the negative second times 1 minus 2. So this would essentially be a positive number times a negative number. It's lagging. Sorry, I'll slow down. It's not lagging for me, so I wasn't noticing. Let me also try to reshare. That can sometimes help a little bit. But when we plug in 2, we'll get e to the negative second times 1 minus 2. So I'll try to slow down a little bit, but also keep talking about it. So we have essentially a positive number since e to the anything is positive. And then 1 minus 2 would give you negative 1. So that will be a negative number. So you don't necessarily need to figure out the number. But if you are curious what the number is, it would be, whoops. It would be negative, oh my gosh, why do you do that? It would be negative 0.135. Well, now it's lagging for me. Negative 0.135 eventually. So that means that when we plug in 2, we get a negative. So I would come back to the number line and put a little negative above the 2. Which I like to do my little line segment little pieces. So if the derivative is positive, we're increasing, and if the derivative is negative, we're decreasing. So I've kind of run into my extra space, but at least help me a little bit. So that would mean that this critical point of x equals 1 turns out to be a max. So we would have a local maximum. Whoa, where'd that line come from? At x equals 1. And so I'll pause for a couple seconds in case of lag, and also so people can catch up with their brains. We're not done this question yet. We still haven't found the inflection points. And let me scroll up to get the rest of this work that we've done so far in here. But we have found the extrema. There was only one extrema. It was a maximum at x equals 1. Remember, 98% of the time, you only care about the x value. You don't care about the y value. Personally, if I want the y value, I will be very, very specific about it. And I think Wiley is pretty specific about it as well. All right. So now we need to find inflection points. So with inflection points, we need the second derivative. So with the second derivative, I have a couple choices, not really choices, but we had a couple of different forms of the first derivative. I'm personally going to work with this kind of middle thing that we had. I think using the less simplified derivatives are easier to find the second derivatives from. Well, it depends on the question. But anyway, here, so if I were, oh my goodness. I could totally use this e to the negative x1 minus x. That would be a product rule. I'm going to get a product rule in what I'm doing anyway. But I'm personally going to use that e to the negative x minus x e to the negative x form to find my second derivative. So, finding our second derivative. Derivative of e to the negative x is e to the negative x times -1, so I'll put the negative in the front. And then we have minus, and it's going to be the derivative of x e to the negative x, which is going to be a product rule. Sorry, I stumbled on that a little bit. And our product rule here is actually going to be the same product rule that we already did. I've already got, you know, the little table guy for, oh man, the little table guy from when we essentially did the same exact thing for the first derivative. Oh, come on, come back. So I kind of already have it worked out, so now I've just got to write it down. So our derivative for x e to the negative x was e to the negative x plus x times negative e to the negative x. Let me just explain. So I need to do a little bit of simplification here, just for the sake of the next step. So one thing is I'm going to distribute this negative on the outside of the brackets. So we'll get minus e to the negative x. Now technically there's also a negative here. Oh, lag. Where's the arrow I did? Come on, little arrow. You got it. There it is. So there's a negative inside the brackets, inside those parentheses. So when I distribute the negative, it's essentially going to cancel out that other negative that's already in there. And we're going to end up with plus x e to the negative x. Hopefully that made sense. And then one more thing to simplify this, well, I guess two more steps, but notice that we have negative e to the negative x and then minus e to the negative x. So that'll give us negative 2 e to the negative x plus x e to the negative x. And then just like last time, they both have an e to the negative x in them, so I'm going to factor that out. So the derivative I'm actually going to want to work with is going to be e to the negative x, negative 2 plus x. And now I'll scroll down a little bit. Well, hold on a couple seconds. So we've found our second derivative. At this point, if you wanted to use the second derivative test to find your extrema, you could totally do that. Essentially, let me just write that out super quick. I'm going to write it in another color though. So if we were to use the second derivative test, we would have been plugging in that critical point of 1 into the second derivative. So we would have had e to the negative first, negative 2 plus 1, which gives you a negative number, but let's see what that negative number is. Negative 0.367, so on and so forth. So a negative means that it's concave down, which would have meant that it's a max, which we already knew. But anyway, if you wanted to use the second derivative test, you could have done that at this point. But I need to find the inflection points. So just like with the extrema, now that we have this derivative, the second derivative, we have to set it equal to 0 and figure out if it's ever undefined. Equal to 0, undefined. Undefined piece is going to be never for essentially the same exact reason as the first derivative. Technically, we do kind of have a sneaky derivative, sneaky denominator, sorry, but e to the x is never equal to 0, so that's never undefined. But we do need to set it equal to 0. And we do kind of have those two pieces again, so either e to the negative x equals 0 or negative 2 plus x equals 0. E to the anything is never 0. Whoop, lag. And then from the other piece, you'll get x equals 2. I know, these are long. I've been doing this problem for like 10 minutes. And then we have to do our second derivative number line. And then we're done this problem. So we have 2, and we need to pick our test points. Now remember, for inflection points, this is kind of the only option you have. You find the number line and you figure out if it changes sign. So we have to plug in 0 and 3 to the second derivative. We'll get e to the 0 times -2, and then e to the -3rd. -2 plus 3 will give us 1. So we'll get -2 when we plug in 0. And we'll get whatever e to the -3rd is. That's 0.05 if we round. So we have a negative at 0 and a positive at 3. Kind of run out of space to write the answer. I guess I'll squeeze it up here in this little box that I just drew. Oh my goodness. So note that the second derivative changes sign there. Now the nice thing about inflection points is that it doesn't matter kind of which way it changes, unlike with the extrema, as long as it changes in general. So we do have an inflection point at x equals 2. And now we're done this question. Actually, let me box that local maximum statement too, so that we remember where the Haley, we've had I guess there wasn't one where it was undefined. We've had ones where we've had to consider it, but we haven't looked at one yet where it actually was undefined. I know 100% sure that the next one is not also. I could try to think of one at the very end of class. The only thing that's going to be different is whatever number you get from that piece is also going to go on your number line. That's the only difference that you have there, is if you set the denominator equal to 0 and you actually find a number, that number just also gets onto your number line. But I can try to pull one of those off the top of my head. That'll be dangerous at the end. But it doesn't really change much. It just adds extra points onto your number line. Are there any questions on that one before we go into the next one? And this is the last one that we have to go over today. And then if we have extra time, I can do other things like Haley just asked. Okay. All right, same idea, all extrema, all inflection points. So need some derivatives. And let me actually split it up this way. That'll hopefully make me actually save space. So we need the derivative. So we got some power rules going on. So bring the power down, we'll get 15x to the 4th minus 15x squared. Always suggest pulling out the greatest common factor. In this case, both of those terms have a 15 and an x squared in common. So we can pull out a 15x squared and be left with x squared minus 1. Then you want to set the derivative equal to 0 and find if it's undefined. In this case, it's never undefined. Also, Haley, the large majority of the ones that we do handle aren't going to be undefined. It's just something that we do need to check in case of that one tiny chance that it is. Yes, I can share my screen again. There we go. So it's never undefined. There's no denominators floating around. We have a product of things. That's also kind of the point of pulling out the greatest common factor. It makes this setting it equal to 0 a bit easier. So we can set the 15x squared equal to 0, and then x squared minus 1 equals 0. Because remember, you can't multiply things together and get 0 unless one of those things was 0. So we'll get x equals 0 from the first piece if you divide by 15 and square root both sides. Or sometimes you can just kind of see that it's going to be 0. And then we'll get x squared equals 1. So x equals plus or minus 1. Remember, whenever you square root something, you pick up a plus minus. So we found the derivative. We found all the critical points. Now we go ahead and plop the critical points onto a number line. So -1. Goodness gracious, 0. I've got the hiccups. Okay. Hopefully they're gone. So we picked points. This is kind of the first time where we've had to try to, where we've had to pick a, not necessarily gross test point, but we can't pick an integer because we need something between 0 and 1. So I will personally pick 1/2 and -1/2. And then, I don't know, I'm going to go with, let's just be nice and do 2 and -2. Remember, it doesn't matter what numbers you do. And sometimes if you, go really large and pick obnoxiously large numbers, sometimes it's easier to see what the sign's going to be without plugging it into your calculator. But anyway, so we need to plug all of these into the derivative. Almost wrote the wrong thing there. Those decimals are very large. And I did specifically leave myself a little bit of space because I know I like to write my little, whatever they're called, line segments. So wait a minute, what was my derivative? My derivative was 15x squared because I scrolled past it. X squared minus 1. Okay. Oh, it's lagging super hard. There we go. Okay. So we've got to take all of these and plug them into our derivative. So 15 times -2 squared, -2 squared minus 1. 15, well, you get the point. Can I not write them all out because I'm lazy? I want to talk about the sign thing really quick in case people like that way, and then I'll just write out the actual number if people don't like the sign way. But remember, since we don't need to know the actual number, sometimes you can just talk yourself through like what the sign's going to be. That 15x squared, no matter what we plug in, is always going to be positive. So like this is always going to start out with a positive value. And then if I think about this inside here, I'm essentially going to have 4 minus 1. Well, that's going to be a positive value. So we're going to have a positive number. If you're curious of what the number is, if you just punch that into a calculator, you would get 180 if I did that right. Yeah. And then if we plug in -0.5, that 15x squared is still going to be positive. If we're doing the sign way again, I'm going to do both. And then essentially inside the parentheses, we would have 1/4 minus 1. So a little tiny baby 1/4 minus 1 down there, which would lead us to a negative. So we're going to get a negative answer here. And what is that answer? That negative number, it is -2.8125. Let me think about that, Kai. I haven't thought about how much. Let me think about that for a second. Let me finish this really quick. If we plug in 0.5, the 15x squared is going to be positive, and essentially we're going to get negative, 1/4 minus 1 on the inside again. So this is also going to be negative. It's also going to be -2.8125. And then if I plug in +2, we're going to get a positive number times a positive number because it'll essentially be 4 minus 1. This will also be 180. Not all functions are going to kind of be that symmetric. Notice how my numbers are kind of the same in each case. That's not always going to happen. So we would have when we plugged in -2, we had a positive, then a negative, then a negative, then a positive. So if I want to do my little number line, my little line segments is what I'm looking for. I would have increasing, decreasing, decreasing, and then increasing. Also, if you want to just I personally move them back up If you want to just like keep going down, if it's decreasing and decreasing, you could totally do that. Personal preference, I just like to keep them close to the number line. Kai will answer your question. Just let me finish this piece. So now that we have that, remember that we have a max or min only when it changes sign. So we have it changes sign at +1 and -1, so the opposite way that I circled them. So at x equals -1, we're changing from positive to negative, so the original function is increasing and then decreasing, so we would have had a local maximum. And that x equals +1, we're changing from negative to positive, so the original function was going from decreasing to increasing, so we would have had a local minimum. So someone asked, do we have to plug them all in on the exam, or can we just write the sign? I would like you to do one of two things. You know, so say it was, in this case, on an exam. This question was on an exam. If you like to just plug them in and just write the values, totally go ahead. So this would be acceptable, or I'll have an or in a second. I am randomly muted, thank you. So I think I accidentally pressed it, not random. But anyway, so one acceptable thing on the exam would be actually write out the values. Another thing I'll accept, I do want you to kind of note all of the things that you've, found. But if you want, say you kind of use my sign idea and you don't actually find the value, just, tell me whether they're positive or negative, greater than 0 or less than 0. Or you could even write positive and negative, that kind of deal. So I do want to see the fact that you're thinking about plugging these into the derivative and then looking at what the value is or the sign of the value. So I do want you to show me that somehow. But as long as you just note that in some kind of way, you don't have to have the actual value if you don't want to. Because I know personally when I do these myself, sometimes I don't find the actual value. Hopefully that makes sense. Okay. We aren't on this question yet. We've found the extrema. We haven't found the inflection points, but we're almost done. So almost there. Now I just gotta erase this stuff real quick. So for inflection points, we need the second derivative. So this is another case where it might have been not too terrible to use the second derivative test for the local maxes and mins. I can go back and write that down when we get the second derivative in a second again. But for the inflection points, we need the second derivative. Again, I'm kind of going to go back to this more unsimplified version of it to find the second derivative so that I don't have to do a product rule. So 15 times 4 would give us 60x cubed minus 30x squared. Again, pull out a greatest common factor. They both have a, whoops, that should be a 30x, not 30x squared. Whoops, minus 30x. They both have a 30x in common, so I would suggest pulling it out. Makes the next step a little easier. So 30x times 2x squared minus 1. Once it's done lagging, there we go. And very similar to what we had to do for the first derivative, we have to set it equal to 0. And I'm just going to write never undefined because it's not. But just to remind us that we took care of it. Gosh, don't do that. Scrolled up more than I thought it did. There we go. Since it's factored out, I kind of have those two pieces that I said equal to 0 separately. So 30x equals 0 and 2x squared minus 1 equals 0. So we'll get x equals 0. And this is going to be our first, not terribly gross, but a little gross number. So we will get that x is equal to positive and negative square root of 1/2. Oh, once it catches up to me. There we go. Now, I know in general, you really shouldn't leave a fraction as a radical, because then technically you have a radical in a denominator and you should rationalize denominators and blah, 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 blah. Yeah, I don't care. So that's an algebra thing. We're in calculus. It doesn't really affect this question at all. So I'm just going to leave it as a square root of square root of 1/2. Once we have that, we plug them onto a second derivative number line. In this case, unlike the extrema, we don't really have a second option. We don't have a, so with extrema, you have a first derivative test or a second derivative test. For inflection points, it's pretty much use a second derivative number line. That's pretty much your option. This square root of 1/2 and negative square root of 1/2 is about 0.707, just so we know what kind of test points we can pick. So I'm going to pick 1/2 and negative 1/2 again. And then maybe just 1 and negative 1. And then just to save a little bit of time, I'm just going to write down the actual values. I'm not going to do my little sign hoopla. But you can always talk yourself through that if you like that way. But let's just find the actual values. So negative 30 times, oh wait, that has to be in parentheses. F double prime of negative 1 will give us negative 30. And then F double prime of positive 1, I'm going to jump down really quick, will give us positive 30. And then plugging in negative 1/2 will give us 7.5. And then plugging in positive 0.5, I believe gives us negative 7.5. Let me double check. Yep. Again, kind of a pattern to those answers, but it's purely coincidental. So we have, when we plug in negative 1, we get a negative, and then we got a positive, and a negative, and a positive. So if you wanted to do a similar thing to the little line segments, sometimes I do little concavity pieces. Sometimes I don't. It's not really as helpful for this one, this inflection point piece. But if you like it, go right ahead. So now, essentially, remember, an inflection point, it just has to change sign in general. So unlike the maxes and mins, we don't care how it changes as long as it changes in general. So we have that essentially at all three of those points that we found. The negative 1/2, negative square root of 1/2, the 0, and the positive square root of 1/2 are all inflection points. We have inflection points at x equals 0, and I'm going to write it as positive negative square root of 1/2. So let me zoom out so we get all of this question and all of its pieces. So let me just because I did it on the last one. So if we were to do the second derivative test here, we would have had to plug in negative 1. Actually, this is probably a good one to note something, so I am going to do this. So if we use the second derivative test, we would have gotten essentially negative 30 times 1, so negative 30. Oh, well, I already knew that because I plugged it in over there. So that would be less than 0, so it would be concave down. So we'd have a max, which we did find. And then I ran out of space, so I'll just write it over here. And then we'd have to plug in, I'm going to plug in +1 next, which would give us +30, so that's positive, so concave up would give us a min. But notice what happens when I plug in 0. I would get 0 times -1, which is 0. If I plug it into 30x times 2x squared minus 1. So remember, when the second derivative test gives you 0, it's inconclusive, and we would have had to use the first derivative test anyway. So actually, this wouldn't have been a good one for the second derivative test, because you would have had to go back and find the sign chart anyway. And so yeah, that giving you 0. Now, you shouldn't think that just because you get 0 from the second derivative test means that it's nothing. Like 98% of the time, that's going to be what happened. But there are very, very rare cases, and don't ask me to think of one because I won't be able to. But in life, there exists a situation where the second derivative test would give you 0 and something weird goes on. But anyway, so the second derivative test would have gotten us the local max and min, but we would have still had to go back and double check that 0 with a number line. So that one would have been not great to use the second derivative test for. Anyway, so that's that one. Someone in my last class asked me how many of these are going to be on the exam. Ones like these where you have to do both types of things, only one of them. But I could have, maybe one question where I just ask you to find the extrema, and then one question where I just ask you to find the inflection points or something like that. But one where I'm going to ask you to find both sets of things for one function, there will only be one of those. So anyway, that's all the content we needed to go through. We have 10 minutes, so if anyone has any questions, Haley, do you want me to do one where the denominator is actually, the derivative is actually undefined? Or are you kind of just cool with they get plopped into the number line? Okay. Yeah, it's really just whatever numbers you get from that, you just plop them on the number line and you just have more things to test. That's the only thing that changes. But if anyone has any questions, any more ideas you want me to go over again, any homework questions maybe you're struggling on, maybe you've already looked at a couple of them. How many questions are there on the exam? I haven't completely finalized the exam yet. I'm close, I'm almost done. And if I count up all the pieces that I have now, because sometimes my questions come in like part A, part B. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15-ish. Because some of these can take a bit of time, like the ones we just did. So there looks to be approximately 15 questions. It's looking like on the exam. Oh, Emily, are you here? Are you having a review? Question mark, question mark?
I was just typing it as you asked that. I'm gonna have my session tonight and my session tomorrow from 6 to 6:50. Instead of like 1 2-hour one, I'm gonna split it up into 2.
Okay. Cool. So feel free to put that in chat also. But yeah, Kai, I gotta pull it up real quick, but I can do that. Why is 1 and -1 the local max and min? Sure, I can talk about that while I'm pulling this up. So we have to see how this derivative changes sign at that point. So notice in our number line at -1, the derivative is positive to the left and negative to the right. Now the other thing we need to remember is the relationship between the derivative and the original function. So, and that's, I'm pretty sure we wrote that at the very beginning of these notes. Yeah, right here. So this is kind of what we're using to figure out if it's a max or a min. This kind of relationship between increasing and decreasing and positive and negative for the derivative. And down here a little bit, kind of lays it out as well. So essentially, if we have that the derivative changes from negative to positive, then the original function is decreasing in that first bit and then increasing in the second, which is why I kind of draw those little line segments. And then likewise, but in a slightly different way, if the derivative changes from positive to negative, the original function was increasing and then decreasing. So if we're in this kind of situation over here where it went from negative to positive, we must have had a min because the function must have been going from decreasing to increasing. And the only way to go from decreasing to increasing is if you hit a min. And then the opposite way, essentially, if your derivative changes from positive to negative, if your derivative is positive, then your original function is increasing. And then if it's negative, it's decreasing. So we essentially went from positive to negative. So if it goes from positive to negative, we must have hit a max. So down in the example you're actually talking about, I think it was Ty. Got it? Okay, cool. Then I'll stop babbling. And Kai almost got this pulled up. I know other people asking questions. I will get to them when I can. But Kai wanted to see number 4. I assume you just mean like the 4th question, which is okay. Come on. Now I just gotta wait for Wiley to load. There we go. Do. And I should come over here. So this is 4.1. Number 20. So this is the one you were asking, Kai. This is very similar to the first one we did today. So here we want to find local maxes and mins. Now my function might be slightly different than yours because Wiley sometimes switches up the numbers. So I think the only thing that would change would be that 6, but maybe it's also what you have. Anyway. So we would need to essentially find the critical points and use our little number line. So we need the derivative, which is a product rule, where essentially we have f is x and g is e to the negative 6x. So f prime is 1 and g prime would be e to the negative 6x times negative 6. So our full derivative I'm going through it a little quickly, but it's also, we don't have a ton of time and these questions take a while. Both of those terms have an e to the negative 6 in it, so I can essentially factor it out and be left here. And then we want to set the derivative equal to 0. So we take our pieces and we set them equal to 0. E to the negative 6x is never going to happen. Again, e to the anything is always greater than 0, so that's never going to happen. And here we'll get 1 equals 6x, so x equals 1/6. So then we put that on a number line, so 1/6. Pick some test points, maybe 0 and 1. Take those test points, plug them into the derivative. We get e to the 0, 1 minus 0 would be a positive times a positive, or just equal to 1. So that's going to be a positive. And then we'll get e to the negative 6, 1 minus 6. So we'll get a positive times a negative. So a negative, I don't know what, so e to the negative 6 times negative 5, negative 0.12. So we get a negative there. So our original function would have been increasing and then decreasing. So that means that x equals 1/6 is going to be a max. And we don't have any mins. So essentially for Wiley, what you would do is that in the local maximum box, you would type in 1/6, and the minimum box, you would type in NA. Cool. I know I went through it a little fast. I think Emily told you how to find the SI sessions. So Haley, 31 and 30. Wait, what? I don't see a 31, Haley. I see a 32. Haley. "31 is in section 4 point." Oh, that one. Can't see. And question 32, though, I think you said. So the 32 one, 4.1, number 32, you need to be slightly careful with the notation. So essentially that one, oh, I love that one. Anyway, so in 4.132, I'm going to give a hint and then move on to the next question because the hint should be enough, and we're also out of time. If anyone needs to go, feel free to bye. You're going to get something that essentially has a denominator in it. And when you type it into Wiley, you'll type in, this is not the answer, but it'll look something like, I don't know, 7 over 5 times 4. And you would have to put the whatever's in the denominator in parentheses. So that's a hint for 32. It's usually just notation. I can also look at that on yours later, Haley, and email you about it. But I want to talk about the other one because I think Anne's kind of asking about the same thing for that graph one. I love that question. I love it a lot. So that question that you're talking about with the graphs. Oh Lord, I gotta try to draw this. Oh man. Pretend that hit the x-axis, and we have a point. Technically went over there. We have a point here. We got 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 a point here. So I'm going to start with the last piece of this question because I think that's what Anne is asking as well. So it asks this question like essentially 3 times depending on what the graph is actually looking like. So in the third piece, you're considering this to be the second derivative. And in all cases, you want to know where f has inflection points. And this goes way back to that chart that I said was really important. So if I can write this super quick, positive, increasing, negative, decreasing, positive, negative, increasing, decreasing, concave up, concave down. I'm also going semi-fast because I have a meeting in a little bit, so I gotta run. But so if we want to talk about this being the second derivative, but still want to talk about the inflection points of the original function. So an inflection point is where a derivative changes concavity. Now think about what we were just doing in the chapter 4 material. What did we do to find the inflection points? We found the second derivative, we set it equals 0, and we figure out where it changed sign. So if this is the second derivative, the thing we want to start with is where is the second derivative equal to 0? So it's equal to 0 there, there, and there. But not only does the second derivative have to kind of be 0 around that point, but it also needs to change sign. So it must change from positive to negative for there to be an inflection point on the original function. So the only 2 that actually change sign are those first 2. Because that last one, it just kind of touches the x-axis, but then goes back up again, so it doesn't change sign. But to have an inflection point, the second derivative has to change sign because the original function has to change concavity. So that would be the answer to that like third part of that question is just those 2 that I have circled right there, where the second derivative is 0 and it also changes sign there. really quickly, if we go to the first derivative part of that one, so the original function is going to change concavity, but if we look at the derivative, then that would mean that the derivative would have to change from increasing to decreasing. So which points on this graph, now that we're considering it to be the first derivative, where does it change from increasing to decreasing? Well, it changes here, whoops, here, and here, and here. I don't think there will be a question like this on the exam, although I do really, really like it. But it's not currently on the exam. But anyway. So since we had to talk about the derivative, but we wanted inflection points, that would mean that the derivative had to change from increasing to decreasing, so we have those 4 points. Really quickly, if we change this to the original function, we then just want to look at where this changes concavity. Now that's harder to see. Now this piece is concave down, this piece is concave up, this piece is concave down, this piece is concave up. So I've kind of circled the very obvious pieces for concave down and concave up. So if it changes somewhere between those circles, each pair of circles must be where our inflection points are. So our inflection points are going to be here, here, and here, the things that are circled in blue, if that's the original function. Because if we're looking at the original function, then we do just want to look at where it changes concavity. Lorenzo, I would love to do one, but I have a meeting right now. What I'll do is I'll write one up and I'll email it to you so you can see it worked out because I don't have time, unfortunately, right now. I got to run. Yeah, sorry, I'm trying to scroll through everything else that people have written. Is there anything on the test that isn't on the exam review? No. No. Ooh. Maybe. No, wait, I did put one of those on the review. Never mind. Ooh, did I put one of those on the review? Oh God, I can't remember. 1 second. I can answer it really quickly. Did I put one of those? Did I? I did. Okay, so no, it doesn't look like there's anything extra. Looks like everything that is on the review. Well, maybe there's stuff that's on the review that's not on the exam, but anyway, I'm not finding anything on the exam that's not on the review. So I have to run. Lorenzo, if you don't get an email by like the end of the day, remind me, but I'll get that to you when I can. All right, gotta go, guys. Bye. I gotta stop recording.